So today's lesson is kind of an intro lesson. This shouldn't take overly long. Both the last two classes we were done in about 20 minutes, 30 minutes. What I want to do is introduce to you our new unit, describe what we're going to be up to, and there's really just one concept and one formula we need to learn. So this is not an overly long lesson. This is going to be our new unit. Our unit is on something called oscillatory and circular motion. And most other physics teachers, when I talk to them, they actually separate these two into two different units. They do a unit just on circular motion. They do a unit just on oscillatory motion. And I like to put them together. And here's my why as to why I do that. Do you guys know what the word oscillate means? If I told you that something is oscillating back and forth, it literally means it is going back and forth, like a pendulum, like I have on this slide right here. That is something that is oscillating. It's going back and forth and back and forth. And one of the unique properties about things that oscillate is we can time how long it takes to go back and forth. So I'm just going to wave my hand back and forth right here. I would say that it takes about 1 second for me to go there and back, and there and back, and there and back. And that's known as a period. A period is basically how long something takes to cycle. Right? Anything that cycles in a repetitive nature has what's known as a period. For example, Earth has a period, 365 days. 365 days for the Earth to go all the way around in one circle. Or if I were to talk about the period of, say, moons, we can actually plan on when there's going to be a full moon, when there's going to be like the half moon, the little sliver moon, right? There's like a pattern to it, and anything that has a pattern to it has what's known as a period. So things that oscillate back and forth, they have a period. But so do things that go into circles. If you can imagine a pendulum swinging back and forth, like you watch me using my hands here, well, what if I swung this thing so far back and forth that eventually it started going into a circle? Well, this also has a period to it, because now I can measure how long it takes to go in a full circle. So anything that either oscillates back and forth, or anything that goes in a full circle has a length of time that it takes to repeat itself. Physics term for that is a period. Okay. The word we use is this bolded one right here, periodic motion. Anything that has like a same regular interval is periodic. And we're going to work on two different types of functions. One is going to be known as the sinusoidal function. One is known as a circular function. And for anyone who's taking a Math 30 class right now, or is about to take a Math 30 class, you're going to learn about this graph in a math class. Some of you guys, you're in Math 30? Have you guys done trig yet? Okay, you will learn this eventually. Everybody else, even if you're in grade 11, if you take a 30 level math class, you're going to be like, oh, Chris talked about this in physics. So this is known as a sine function, where basically what happens is something's going up and down and up and down and up. And this is oscillating, right? Something is going back and forth, side to side, up and down in I don't care what direction, but if it repeats itself, it's periodic or sinusoidal. And the word that we need to discuss today is how long does it take? And that's that word right here, period. It takes this amount of time to go up and down. Maybe as another example, you know how there's that new YMCA coming over here on the corner? There's supposed to be a wave pool in there, right? A wave pool would have a periodic motion to it where the waves go up and down and up and down, right? Isn't that more or less what this picture kind of illustrates to us? So we have been talking so far about linear and quadratic functions. A linear graph looks more or less like this, and a quadratic graph looks something like this. Well, eventually, when you get there in math, it'll match up with physics, but this is known as a sinusoidal graph. It goes up and down and up and down. And we're going to do a lab on this next week, where remember how we're doing regression equations? There's linear regression and quadratic regression. We're going to plot a sinusoidal regression, which just basically goes back and forth. It oscillates. Here are the two main types of devices we're going to talk about in our physics class. One is a pendulum, and I don't really need to probably describe the pendulums too much, because most kids understand pendulums are going to go back and forth for forever, at least until friction slows them down. The other thing that's sinusoidal, though, is a spring. Because if you can imagine that you have a spring that goes up and down, if I were to have like an elasticy kind of spring here, I can make this thing go down and up and go boing, boing, kind of like a pogo stick. If you can imagine someone bouncing on a pogo stick, they're going to bounce up and down. A trampoline would do the exact same thing, right? It's kind of got a spring to it. They bounce up and down. So, as another way of kind of illustrating the math overlap, which I know not a lot of you have gotten there yet, but you will, this is that same up and down sine graph. If I turn it sideways, can you envision how this is like a pendulum swinging back and forth? Here the pendulum is swinging out and back, then to the left and back, then back to the right and back. This is your pendulum swinging back and forth, but I've turned it sideways as a way of trying to illustrate that. One of the terms that I need you to know as like an introductory word is the word equilibrium position. Equilibrium position would basically be like your baseline. It would be, well, like right through the middle. This straight up and down vertical line right here is equilibrium because then it swings out to the right and back, and to the left and back, and to the right and back, and to the left and back, and you just repeat for forever. So hopefully that makes sense. You guys okay? Okay, so here's the formula we're going to learn today. It's fairly straightforward. It shouldn't take too long. The words we need to know are period, which I've already discussed, and then the word frequency. And maybe before I discuss this slide, I found that with my last two classes, if I go to this slide here first, this slide here helps me describe period versus frequency better. So imagine that I've got three different graphs here. And imagine that I just kind of made this right here be, say, 1 second. So like from here to here, that was horrible. Let's make that be 1 second. If I were to ask you what the period is of this first graph right here, the answer for the first graph for period would be 0.33 seconds. And the reason why it's 0.33 seconds is if from here to here is 1 second, then for this thing to go down and back up, that must have been 0.33. Then to go down and back up again, that would have to be 0.33. And if this went down and back up another time, that would be 0.33. And if I added a third plus a third plus a third, wouldn't that basically be 1 second? You know, minus the rounding part that we're ignoring. This would be known as your period. It's how long it takes to go there and back. How long does it take to go there and back? How long does it take to go there and back? So if I'm just telling you that from here to here is 1 second, then each of these is a third of a second. Well, that's period. Frequency in this example would be 3. The reason why it's 3 is frequency basically says how often did something occur. I'm not asking you how long it took. Now I'm asking you how often is something happening. And hopefully you'd agree that right here there were 3. Well, let's do it like this. There's 1, there's 2. There were 3 iterations of something happening, so therefore my frequency was 3. These two numbers right here are linked by what's known as the reciprocal relationship, which is back here. A period is always 1 over a frequency. And so if your frequency is 3, then your period is 1/3. For those of you who've done this in your math class before, this is the graph of y equals 1 over x. And it kind of looks like this right here, where if x is 3, y is 1/3. Let me try another example, see whether I can solidify this. Let's use this next kind of example right here of a wave going up and down, oscillating back and forth. What is the frequency of this second wave here? 4. Why is the frequency of this wave 4? Well, it went up and down here once, oh goodness, once, then twice, then 3 times, then 4 times. So I would say this thing has a frequency of 4 times. But remember how I told you that from start to finish was going to be 1 second? Well, then how far was each wave? Well, this would be 0.25. This right here would be 0.25. This right here would be 0.25. And this right here would be 0.25. How did I know that? Well, your period is always the reciprocal of your frequency, which is 1/4, which is 0.25. If I add 0.25 plus 0.25 plus 0.25 plus 0.25, I get 1. So let's try one more example. On this bottom one down here, what is my frequency? It's just over 7, I think, because it goes up and down once, twice, 3, 4, 5, 6, 7, and it's kind of on the way down a little bit. So you could say that the frequency of this might be like 7 and a bit. I think it's technically 7.25 because here would be a quarter. This would now be half of the way up and down. This would be 3/4, and that would be the full rotation. Can you kind of see how that works there? So this would be a quarter of the way down. Then this would be all the way down. That's half of it because you got to come back, right? Then this is 3/4, and then all the way back. So this extra little bit would be 7.25. We've done 7.25 iterations of this pattern. So therefore, if I asked you how long is it between all of these, you would just go 1 divided by 7.25. Oh, where did I leave that calculator? Here it is. 1 divided by 7.25. So that means it's basically from here to here is 0.14. And from here to here is 0.14. And from here to here is 0.14. And if I add all those up, we'd have a full second. So let me recap here. Period is how long it takes for something to occur. Period is how long it takes for something to occur. Period is how long it takes for something to occur. Period is how long it takes for something to occur. What was the period of what I just said there? Maybe about 3 seconds. Right? It took me about 3 seconds to say, period is how long it takes for something to occur. What was my frequency, though? How many times did I say it? I think I'm up to 5 now total. Yeah. Do you see the difference between the two? Yes. Yes, okay, I'm going to get to that next. Yeah. So, but if we're okay with this concept, period is how long something takes, and then frequency is how many times it happens. So if I say it 5 times, we have a frequency of 5. Then Taya's right, though. The next question should be, though, well, what are we measuring that per? Did I do it 5 times in a minute? Did I do it 5 times in a year? Did I do this 5 times in a decade? Right. So the way frequency technically works, if I can go back here, is it's the amount of times you cycle through something, usually per second. Okay, we usually measure things per second. And the unit we have when we measure it per second is known as a hertz. Capital HZ tells you how many times you cycle through something per second. So if I go back to this example right here, we actually had a frequency of 3 hertz, a frequency of 4 hertz, and a frequency of 7.25 hertz because I told you this was happening in 1 second. A more common unit of measurement, though, is this one back here, RPMs. If you have a vehicle, you probably have a meter on there that reads RPMs, right? 2,000 revolutions per minute, right? A nice safe revolutions per minute to use would be about 2,000 to 3,000. But I mean, if your car has like a red line on it, you guys know what I'm talking about. You're talking about this here, right? A car might red line at 6,000 or 7,000 RPMs. That means you're pushing your engine too hard and you may be at risk of damaging your car, right? Revolutions per minute then tells you how many times is it spinning per minute, right? So frequency is how many times something occurs per unit of time. Right? Let me give you another example here. What is the frequency of your birthdays? Well, it's once per year, or how about 10 times per decade? Say that again. The frequency of your birthday is either once per year. What about 10 times per decade? Doesn't that still kind of work the same way there? Right? You would have 100 birthdays in a century. Right? That's a frequency. So it just depends on what you want to divide by. Let me go through a few more slides. I'm getting close to the end of what I need to do. This slide right here illustrates the reciprocal relationship between the two. If I tell you that you have a frequency of 3, it means the period must be 1/3. And guys, the relationship then is this formula here. Frequency is 1/period, or we sometimes write the other version. Period is 1/frequency. They're both basically reciprocals of each other. And if you weren't aware of the shortcut on your calculator to find that, I want to show you that right now. If this was a basic calculator, let's say that I told you that your frequency was 3 hertz. Well, if you then did this button right here, the -1 button, which is found right above the squared button. Ooh, let's not do both, though. Let's do one or the other. This basically now tells you 1/3. 3. If I give you 4 to the minus 1, this is now 1 over 4, it's 0.25. If I did 2 to the minus 1, this would be 1 over 2, which should now be a half. And if I just could do one more here, if you did 1 to the minus 1, hi. If I did 1 to the minus 1, what would that be without even pressing an answer? What is 1 to the minus 1? Yeah, 1. So I just wanted to show you this. This is a nifty little shortcut so that every time that you need to calculate a reciprocal of something, you can just press to the minus 1 button and it finds it for you in just one quick step. Okay, the other slide I want to get to here just describes some more periodic motion. Okay. Here's some other graphs that are periodic. Okay. There are many scenarios in life that you guys probably already know of that have a period to them. Maybe this one right here is a good one to discuss for a few minutes, though. This is a heart rate monitor. Right? My resting heart rate is roughly 60 beats per minute. Right? That would be a frequency, 60 beats per minute. Right? But I could also write that as 1 beat per second. You guys see how 60 beats per minute is the same as 1 beat per second? Right? And so anything that kind of repeats itself on that pattern is periodic. Here's one that really applies to my wife's line of work. The dog's a little distracting, apparently. Just a little bit. Have I shared with you guys before that my wife works on labor and delivery floor at the hospital? So Melissa works on the floor where the pregnant moms have babies. And one of the challenges that she has on that floor is trying to make sure that she always says she has 2 patients. She has a mom and she has a baby, right? She always has 2 patients she has to worry about. She can talk to and do tests on mom, but when baby is inside a pregnant mom's belly, the best that they can really do is what's called a tracing. That's what she calls it when she's at work, a tracing. And really a tracing is actually 2 different things here. There's a fetal heartbeat where they try to keep track of what the baby's heart rate is. And so if the baby's heart rate is always going back and forth, up and down at a nice even amount, that's usually a good sign. But what if all of a sudden the baby's heart rate spikes and all of a sudden the heart rate starts to vary? Well, now that becomes a bit more dangerous because the baby is now stressed. And when a baby is stressed, then they may want to do a C-section and get the baby out a little bit faster because something's going wrong. The other thing they may want to assess is something known as a contraction. And without getting into the biology of childbirth, if you know what a contraction is, it's how the mom pushes the baby out with contractions of muscles. Anyways, not going that far. But contractions are also periodic because like every 5 minutes, a mom might go through a contraction. And then eventually every 4 minutes, a contraction. And I've had 3 kids now. Once you get to like every 2 minutes between contractions, now the mom's ready to push the baby out, right? Anyways, the point I wanted to make here is that this is also periodic. You've got stuff that's happening every regular interval. If it's a regular interval, that's usually a good thing, especially for my wife at the hospital. You want to have regular intervals. So, makes sense? Okay, let's try 2 math examples, then we're done. I'll get you out of here. First math example, say that there's a hard drive that's spinning at 7,200 RPMs. RPM stands for revolutions per minute. That is a frequency. Let's try to calculate the frequency and period, though, in the metric unit system. So, if I were to write out that we have 7,200 revolutions per minute, we don't usually measure things in revolutions per minute. We measure them in revolutions per second. How am I going to convert revolutions per minute to revolutions per second? Well, you either times or divide by 60, right? I think you first said times by 60 and then you changed to divide. Let's just talk through, though. If you were to times this by 60, you would get a massive number. Like, let's just do the math here real quick. What is 7,200 times by 60? If you did times by 60, you'd get 432,000. Would that be how many revolutions per second would be logical? I mean, if you have 7,000 revolutions per minute, you don't have thousands more revolutions per second. So timesing by 60 was wrong in this case. We need to divide by 60. If you take 7,200 and you divide by 60, hopefully this is more logical. You're going to get 120 revolutions in a second. If you spin it a lot of times in a minute, it won't spin quite as many times in a second. It's the prorated portion, but it's less. Right? But what I need you guys to know is that 120 revolutions per second is what we call a hertz. H-E-R-T-Z, hertz. It's named after the physicist Heinrich Hertz, by the way. So that's its frequency. Well, if I were to ask you to calculate the period of this spinning disk, the question is basically, how long does it take for it to go around once? Well, if it's spinning around 7,200 times in a minute and 120 times in a second, the length of time is going to be pretty small, isn't it? Right? This thing is moving pretty quick. So the fast way to go from a frequency to a period is just do the little -1 trick. Your period is 1/120th of a second. Does that make sense? If the frequency is 120 times in a second, the period is 1/120th of a second. So if I take 120 and go to the -1, I get this value here. It's 0.0083 seconds, which makes sense, right? It's going to spin around once in a blink of an eye because it's got to go like crazy to do 120 in a second or 7,200 in a minute. So quick recap. Period, how long something takes to happen once. Frequency is how many times it can happen per measurement of time you want to go with. We normally want to go per second, so hertz. Sound good? Yeah. Yes. Typically the units for a period would be seconds, so I've got an S right here for seconds. But it could be minutes, it could be hours. I've got another example here that might illustrate this. Let's try this last one, and then we're done, by the way. Let's try to figure out just the basic period and frequency of these 4 scenarios. Okay. Scenario 1. What is the period and frequency of a minute hand on a clock? How long does it take? And let's make this one A, I think, just to help organize it. How long does it take for the minute of a hand of a clock to go all the way around? The minute hand of a clock. 60 minutes. That'll work, right? Because the minute hand of a clock goes all the way around in 1 hour. That's the period of a minute hand of a clock, right? 1 hour. Or I could make that 60 minutes. Or I could make that 3,600 seconds. Really, all of those would be a valid way of describing the period of a minute hand going all the way around. It happens like clockwork. That's literally where the word comes from, right? Like clockwork is a periodic function. Now, if I wanted to calculate the frequency, the best one to use would be to make this guy right here go to the -1. Because if I took 3,600 to the -1, I'm going to get 2.8 to the -4 hertz. And I just want to spend a second discussing how this works here. A hertz tells you how many times something cycles in a second. In 1 second, how far did that minute hand move? It really didn't move at all, right? We would need a whole hour for the minute hand to actually do a full cycle. And so if we don't even have an hour, we don't even have a minute, we're talking about in a second, because a hertz is how many times something happens in a second. It's how many times something happens in a second. Did it even happen in a second? No, like a small fraction moved in a second. This number is 0.00028. It moved that far in a second. So it didn't even do nearly a full rotation. So hopefully that made sense for the first one. Let's try another one. I'll just kind of plow through these, and sometimes repetition helps. Part B. A person with a heart rate of 86 beats per minute. 86 beats per minute, is that a period or a frequency? Is 86 beats per minute a period or a frequency? Is it telling you how long it is between contractions, or is it telling you how often the contractions happen? How often? We know that 86 times in a minute we get a contraction of your heart, right? So if I were to go down here to part B, I know that my frequency is 86 beats per minute. We don't usually measure things per minute, though. We usually measure them per second. Is your heart beating faster or slower than 1 per second? Is your heart beating faster or slower than 1 per second? Faster, right? Because 60 beats per second would be exactly 1 second each, right? So maybe what I could do is I could divide this by 60. And if I took 86 and divided by 60, I would now have 1.43 beats per second. And if it's ever something per second, we write it as a hertz. So the frequency of this person's heart is 1.43 contractions of your heart muscle every second. So boom, 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 right? 1.5 times basically every second your heart is beating, give or take. Well, if I wanted you to then tell me the period of your heartbeat, now I'm asking how long between contractions is it? It should be less than a second, right? Because 1 second would be 60 beats per minute. If you have 120 beats per minute, it would be half a second each. So all you got to do is make this go to the -1. So 1.43 to the -1 gives me basically 0.7 seconds. And so yeah, every 7/10 of a second, your heart beats again like clockwork. You follow that? Okay, next one. The Earth. The Earth has periodic motion. Okay. What is the period of the Earth? Well, it's either 365 days to go around the sun. That's the Earth's period. Or if you're talking about Earth spinning on its axis, how long is a day? Why don't we go with that one? Why don't we say that the Earth's day length is 24 hours? But we could have gone with 365 days in a year. So the period of an Earth day, is 24 hours. Or 86,400 seconds. That's the period of an Earth day. What did I do, by the way? How did I get that number? Yeah, times by 60 twice. Good job. Jinx. Good job. Okay, so there's your period. Does the Earth go faster than your heart? No. Your heart beats every 0.7 seconds. The Earth requires a lot of seconds to finally finish its full rotation, right? So for the last step, if I ask you what the frequency of the Earth's rotation is, make that go to the -1. And the frequency of the Earth's rotation is 1.157 to the -5 hertz, which means that the Earth does not rotate very far in a second, right? In 1 second, has the Earth rotated very far? No. Right? If let's say the frequency was 2 hertz, that would mean the Earth was spinning so fast that the Earth spun around twice in 1 second. Isn't it a good thing that the Earth does not spin very fast? What would happen if the Earth spun at a rate of 2 hertz and Earth literally went around 2 full times in 1 second? What would happen to us? We would probably fly off, kind of like when I bring my daughter to the merry-go-round or whatever they function. You know those merry-go-rounds that have like the big teepee kind of structure to them? You ever seen those before? And I spin her around in that. If it wasn't for the fact that there's those big ropes keeping her inside the merry-go-round with the teepee structure to it, she might go flying off of it, right? Anyways, hopefully that made sense. So yeah, we want a very low frequency for Earth spinning. Otherwise, yeah, we'd have problems. Last one, then we're done. Part D, I asked you about a bumblebee which flaps its wings 800 times in 10 seconds. I really don't have a frequency or a period yet here. I mean, I know it happened 800 times, but it happened in 10 seconds. What I want to illustrate with this one right here is that if something flaps its wings 800 times in 10 seconds, as long as we have periodic motion, very regular, consistent motion, then we should be able to prorate this and say that it happened 80 times in 1 second. Can you see how I managed to pull that off? I just basically cut it by 10, right? 810 is the same as 80 in 1. I once took a first aid course, and I was asked to do measure my heart rate. And the first time I did it, I literally counted to 60, and I counted how many beats I counted in a minute. And then the instructor said, Chris, that's a waste of time because then you got to wait for a full 60 seconds. They taught me count to 10 seconds, count how many pulses there are in 10 seconds, and then times by 6. Anybody else ever had to do that before in first aid training? right? Like you're just doing the prorated portion of it. So I'm just rating this back down by dividing this by 10, dividing this by 10. Guess what? This has a frequency of 80 hertz because it's now per 1 second. If I then reciprocal this frequency, I'll have a period. So here, I'll even do it this way. It's 1/80th of a second. Can I put it that way? A bumblebee flaps its wings up and down 80 times a second. So every individual flapping of wings is an 80th of a second, which is 0.0125 seconds. When we are doing our physics labs and I use my video camera to record things, it records frames per second. Right? A frames per second is a frequency. So. Okay, let me wrap things up and then we're basically done for the day. I should be able to get you out of here about 25 minutes early and you can work on what you like. But let me summarize first. I need you to know 2 things from my lesson. The first introductory topic was, do you understand what we're getting ourselves into? Stuff that is periodic. Anything that has a period has a regular, consistent back and forth or round in a circle kind of motion. And that's why I put these 2 units together. Other teachers separate them, but I think they belong together. Anything that has a regular repetition belongs in this unit. So we're going to talk about things that go back and forth or in circles. That's 1. 2, I need you to know the fundamental linchpin of the unit, which is anything that has a period or a frequency. You need to be able to basically work between the 2 of them. As long as you know how to take a reciprocal, we're done. Right? Just make it go to the -1 or go 1 divided by 4. Go 1 divided by 2, and you're good to go. So tomorrow what I'd like for you guys to do then is watch the lesson on harmonic motion. And you can do that tonight if you'd like. You can do it later. But that gives us flexibility tomorrow so that if you want to work on something else during tomorrow's class, you can. Or if you just want to watch the video in class like normal, do that too. So that's all I got. You guys got any questions? Okay. If you'd like to, you're free to go somewhere else. If you're leaving the building, can you make sure you write that down on the board there so that I know where you are just in case there's a fire drill or a lockdown. But if you want to go somewhere else, you're welcome to. If you want to work here, you can. I need assignment 3 before I leave today if you want redos on it. So, okay. Thanks, everybody.